All right. So what I'm going to do on these problems over here, it's the problem six, set six, problem number 2. I'm just going to go through this points A and points B right there. Okay. And then you can come up with whatever angle you like. Let me call this incident angle right here. Every time that you reference, it's the angle with respect to the normal line. So you can name this maybe incoming angle of alpha. All right, I'm just gonna keep going. This one is, I'm gonna name this angle beta on the way out. Okay, so at A, okay, so what you're gonna get is going to be end of the air. I think you get to this point. I don't think it's a problem, right? I think you are okay with this. And end of the glass is just N, and then you have the sine beta. I think maybe what you stuck on this problem is just try to make the theta in form of other things. I think maybe that's what you are so having problems with. But in terms of applying Snell's law, I think it's straightforward. Am I right? I think. All right, try at point B. Okay, at B. All right, so what you can call them, you can call this gamma, and on the way out is already theta. So at B, you're gonna have in glass, and sine of the incoming is gonna be gamma, and it's gonna be on the way out is going to be end of the air, and then sine alpha. Here we go. All right, so the rest is just trying to eliminate everything pretty much. Just sort of like try to get rid of everything. We don't like alpha, we don't like beta, we don't like gamma. We just want to make theta in terms of N, R, and L. So that's all you need to eliminate them. All right, so let's see. I'm not so sure if I can make it nice as well, but let's give it a shot. Okay, so over here, when you draw a normal line, so that normal line will hit the center of this circle right here. Okay, and what kind of property that we can use for those? So first thing first, when you see the alpha on the top, this is going to be your alpha as well. Does that make sense? Okay, so when you see this one, then I think part of it is already done, because when you look at a circle, okay, let me use different color here. Okay, so I'm sorry, look at this triangle. Oh, let me do highlights. Yeah, right there. And there you go. All right. So now you will be able to figure out the sine of the alpha right away. The sine of the alpha will be opposite over hypotenuse. So from that, then I can say sine alpha is just going to be L over R. Does that make sense? That's sort of like an idea of how to proceed. So at least now you can eliminate that sine alpha from the first equation at point A. And that lead you to sine beta. Okay. Now, for the sine beta, so now you take a look at this. And, okay. All right. So if you look at another triangle over here, for the gamma, it's right there. There you go. All right. And you look at the beta. So let me pull that out right there. So you have this triangle over there. Okay, there's a beta up here. There's a gamma right there. And what you know between the two is the outside over here, that's going to be the sum of the two. All right, and I know if I'm going to get stuck here or not. But it's somewhere around here now. Okay, all right. Okay, so what you have here then, what can I do? Let me think about this a little bit, because I want to relate everything back to the theta. What else do I know? Okay, if I can do it. Okay. So the sine of beta and the sine of the gamma. I mean, it might not be that easy. All right, but I can try. Okay. All right. So just move along with me just a little bit. But once I get to some point, then I think I'm going to just pause here somewhere. So if you look at this triangle over here that I just wrote there, so if you really want to attack the gamma, let's stick with the gamma first. Okay, so if you look at the gamma, there is an opposite over here, right there. Okay, let me look at here. Look at the green triangle over here. Okay, and then you will get the idea how to attack this one. Sine of the gamma will be opposites over hypotenuse. You guys with me? Okay. And I can figure out this height right there, the opposites. The opposites is going to be L, the whole length over here. Subtract out whatever underneath right here. And can I find it out? Let me see. Oh, maybe I'm not. See, I'm stuck too. I'm not so sure. I have to sort of like play around with this a little bit. Let me see if I can get that one. I should be. Shoot, maybe not. Yeah, I only be able to solve for the sine alpha. All right, but I think you will start to see I am also stuck, just like you. But that will be something that I can do with it. Just not so sure at this point how. Okay, sine alpha, sine gamma. So what should I do? I want to eliminate the sine beta and sine gamma. Sine. I thought I know how, but it doesn't look like I will be able to. So let me stare at this for a few minutes. If I cannot figure it out, then I'll just gonna stop here. Okay. Okay, let me think about this side. Actually. Hmm. Okay, let's see. R sine alpha. I don't see that either. I might have to do the law of sine angle. All right, then. I think I'm stuck too. I have to think about this a little more. All right, but one thing I want to show is I think the exam question won't be this bad in terms of like manipulating the mathematical functions like this. Yeah, so I think I'm only be able to. I just have to find a way how to link between the sine beta all the way to the sine gamma, and then I should be okay. But what is the connection between the two? I can use law of cosine. Would that help? Sine gamma. Okay. All right. Sorry that I couldn't get through the end either. All right. I have to, I think maybe spend more time with this, but it's somewhere here. I think I've seen this once and then I didn't. What did I do with that? Beta plus gamma back there. Seems like it's there somewhere. Hmm. All right. So in the meantime, maybe just go through next problems first. All right. Don't want to waste your time too much. Sorry about this. All right, maybe I'll pop up sometimes during our conversations here. All right, but anyway, so back to your concerns. So don't worry too much about um, this kind of complications, I think. Okay, so I'm just gonna ask you to apply Snell's law directly. Yeah. Okay. Cool.
Thank
Yeah.
you.
Yeah. Sorry. It's just.
Can I ask another one?
Yeah. Definitely.
If
Yeah.
does others have question? I don't want to.
So feel
Yeah.
free. I think everyone else can join in as well if there are questions along the way. Yeah. Go ahead. Seems like.
My problem is the set 5-2
Okay.
question 10.
Okay. 5, 2. Set 5. Oh, maybe what's going on with my file? Wait a second. 5, 2. I'm missing the 5, 2 at this point. Okay, let me grab that file. Just a second here. I thought I already downloaded it. There you go. Okay. There you go. All right. Okay, so problem 10, you say? Yes.
Yes.
Okay, Joe, you want me to go through this one, right?
Yes.
Okay, all right. So you have a tuning fork vibrating at 512 hertz, falls from rest and is accelerating. All right. Oh, you asked the hard one. I mean, this is just as I said, it's the upper limit of the difficulty level. So how far below the point of release is the tuning fork when waves of frequency 485 hertz reach the release point, given the speed of sound. So the idea of this one is you just want to know. Okay, so let me move on to this one. So this is 5, 2, problem 10. So what you have here is you want to know when will you be able to get the frequency observed to be 485. So you want to know at what speed. So the idea is you drop the tuning fork down here. So this one is the source that's generating the sound, but it's moving away from you. Okay, that makes sense? Okay, so you're observing the sound up here. So you, let's say, up here is the observer, and this tuning forks that is moving is the source. All right, and then we can apply the Doppler effect. So what you want is the observed frequency is going to be, now you can start setting up things here. All right, and then now we have the speed of sound, the speed of observer, the speed of sound, and the speed of the source. All right, and at this point, this is easy for the observer because observer is stationary. So this term goes to 0. All right. And now for the source, it's dropping, it's sort of running away from the observer. Running away, it will make the frequency drop. But because of the velocity of the source is in the denominator, you make things smaller, you pick the positive sign down here. All right, you got that one, right? So this one we sort of okay. Okay, so with this, then we can plug in the value that's already given here. The observed frequency is 485, so that's on your left side. Okay, the speed of sound is already given, and that is 340 divided by 340 plus the speed of that tuning fork that is dropping. And then you know that the tuning fork will generate the sound of 512 hertz down here. It's sort of like off screen here. Let me squeeze that in here. Okay, 512. Here we go. Okay, got that? All right, so from here, you will be able to figure out the speed of the tuning fork. So that means at that speed, you will be able to hear the frequency of that exact 485. So now you come back to the mechanics. So when you're dropping an object, when will it reach that speed? Okay, so that means what you have over here is you have initial velocity. Let me use u for that to be 0. And your terminal velocity, or the speed that you want to figure out at the end of your journey for this calculation, is when the speed reach that v of that s that you just calculated. Okay, and everything is dropping with the gravity pull. So that is the accelerations g that you need to use. So from here, because they want to know how far below, so you want to know the displacement from the initial point down to the point where the speed, oops, sorry, down too far, down to the point where the speed reaches that 485. Okay, so from that kinematic equations, you have S, that's one you want to figure out. The information that you know is the initial speed, the final speed, and the acceleration A is equal to G. Okay, so from here, then you can use V squared equal to U squared plus 2GS. And that will allow you to figure out S equal to what? Does that make sense? Sounds good?
Yeah.
Okay. All right. So I mean, all in all, it's like you think of it like a 2 steps process. So first steps, you apply Doppler effect, try to figure out at what speed that you will be able to hear that given frequency of 485. And then there is a second step, because you want to know how far down that the tuning fork that is dropping will reach that speed. Then you use the kinematic equations just to get to that. Okay, and this kind of question can be like an alternative questions, like they might want to ask you how far, or I'm sorry, how long after you dropping the tuning fork. Then you just change the parameter s into t if you want to know how long does it take for you to hear this frequency, that frequency, on and on. Okay, sounds good. Not too bad. This level is okay. if
So
this one
Ajahn,
if this one shows up in the exam, is that doable?
yeah, Ajahn, so U is 0 and we
U
just
is
find
0.
S.
Yeah, the initial speed. Yeah, because they say it's falls from rest, so the initial speed will be 0. Yes. Yeah. So this one is already gone. That's 0. Yep. So it's gonna be Vs squared over 2G, and that's how far down from the initial releasing point. Okay. All right. Welcome everyone to ask questions or anything, or if you want me to talk about any point, be happy to.
Oh, Ajahn,
Yep.
the internet did differently with Google,
Oh, really?
like so. Yeah,
So what
he
did you
did
do?
velocity final square
Uh-huh.
minus velocity initial square
Okay.
equal to 2 times acceleration time
Times the displacement.
displacement.
Yeah, same thing. Same thing. So they just move this initial speed to the left side. That's all. So it's gonna be final velocity square minus initial velocity square equal to 2 acceleration s. Does that make sense?
Okay.
Yeah, yeah. Same
Yeah.
equation. Same equation. I think it looks like this there. Is that right? Is that what it is? So they are the same equation. Okay. Very good.
Can I ask another one?
Sure. Yeah, you can ask many more if you as much as you want.
Question 13.
13 on this one. Yeah. Okay.
Yes.
Yes. Okay.
What does third resonant mean? Does that mean third harmonic?
Yeah, the resonance means whenever you meet the conditions of creating a standing wave. That's called, sometimes they refer to those conditions to be resonance condition. So it means what we did in class, like for example, when you have a pipe and then you are able to fit a curve in there, no matter what condition that you can fit in, like you can twist one more. Remember that we did this, and then you can keep going. All right, these are all resonance. So whenever you can fit the right amount of waves into a pipe, into a tube, into a string or whatever, those conditions, we can also call them the resonance. There is a resonance happening. So when you have a third resonance, it just means you can call this the first one. So that means it's the first situation that you start to be able to generate standing wave. So this is your first resonance. And then this will be your second. And that will be your third, on and on. Does that make sense? All right. So it's just another way to talk about which mode of the standing wave that you want to refer to. So this one, well, you said about the harmonic, but by the definition of harmonic, it's related to the frequency too. So you might not be able to say this is the second harmonic for all cases of the tube, because we have different type of tube, or we have different type of system. We have one open, one closed. We have open on both ends, or we could have like a string that has like a closed end on both sides. And you have already seen in class that the frequency in each case might not go like 1, 2, 3, 4, 5, right? We have like 1, 3, 5, like just an odd harmonics too. So it might go better with the overtone. I think maybe it's better. Like the second resonance is going to be the first overtone. That is pretty much guaranteed. Yeah, the third resonance will be your second overtone, on and on.
Okay, thank you.
Okay, yes. All right, but good questions. I think I just mentioned too brief in our class because we didn't really sort of like put our effort into talking about resonance that much. Yeah, but I think maybe I just say, okay, sometimes we refer to like natural frequency, and every time that you excite the system, when I say excite, like in this case, you have a pipe, and then you excite by sending the sounds wave inside that pipe. And if there is some conditions that you can hear the sound that is like a loud sound coming out of it, that is a resonance. So that's why resonance is closely connected to the standing wave generation in the tube. They are pretty
So
much the same thing. Yeah.
in the question, it says to middle C. What does middle C mean?
Middle C, I think it's like a musical note when like in a piano, for example, when you play the C at the center of those piano keys, that is a middle C. Then you can go another like that's a high C. You go up one more octave, then you get another C notes again, but it's the next harmonic on those C. I don't know, is that it's not a harmonic thing, but it's a higher C. So you can go like a scale, each one is one octave, and then you move on to the next octave and then the next octave. So the middle C, just stick with the frequency. So it's this one right here, 261.6. That is your middle C. So it's a C note, a regular C note, I would say. Yeah.
So I was confused with part A. Like
Okay.
it's open pipe. Then is it open pipe for third harmonic or is it first harmonic?
Okay. So let's try part A then. So part A, they say, what is the length of, if let's say you treat the pipe to be open pipe, right? Okay, so let me draw that pipe. So it's open pipe. So it's open on both ends. Now let's try drawing this thing. So the fundamental frequency will be the easiest one to draw. So this is your fundamental one. Okay, and this is your first resonance, your first. So you move on to the next. You just do one twist on this one. Then you get to this one. You can name this is your second resonance. Yeah, and that will be your first overtone. And then we can figure out the harmonic in a little bit. All right. And then the third one right here. Then you do one more twist. There you go. Bam, bam, bam. And that is your third resonance right here. Okay. And then what we did was we just counting the amount, the number of loops, right, in our system over here. So what we did before was just, hey, this first case, the fundamental frequency, this one is one loop. Okay. And that one loop is half the lambda equal to the length of the tube. And then you move on to the next one. This one is two loop. So you do 2 multiplied by half of the lambda. And this is 3 loops equal to the length of the loop. 2, the length of the tube. All right. And then once you figure out the wavelength of those standing waves, then you can flip and then try to calculate the frequency. Okay. So F equal to V over lambda. And that would be V over the lambda is 2L. So you just put 2L right here. Okay, same thing for the next case. F is going to be V over lambda. But now lambda for this one is just L. So it's going to be lambda over L. And then you keep going. F is V over lambda. And this one is lambda is 2L over 3. So it's going to be lambda over 2L. I flip 3 up to the top. Okay, and here, all right, I can put 2 over 2 here just to make things like showing a sequence of the numbers that is increasing. As you can see, because this one go with number 1, this go number 2, and this go number 3, then you can say in this case, your third resonance is also third harmonic. Does that make sense? Okay, because it's triple your fundamental frequency. It's 3 times. The frequency is 3 times. So it's also third harmonic. Okay, but then if you try part B, where is the closed pipe? So when they say closed, usually it's not going to be like fully closed, because if they close on both sides, then you won't be able to do anything with it. So when there's a closed pipe, I think it would just mean like one open, one closed. Okay, and then if you try that one, yeah, I can. So think of this like a review as well. So that's kind of good. So here, one open, one closed. So let me draw 3 cases here. So you start from the simplest one is right here. And that is half of the loop. It's a loop over 2 that is equal to the length of the pipe. But each loop is lambda over 2. So it's already lambda over 4 equal to L. So in this case, the frequency will be V over lambda, and that will be V over 4L. You guys with me so far? Okay, so this is your fundamental frequency, and that's your first resonance. Now you do one more twist. There you go, bam, bam. So this one you can see is 1.5 loop. So it's 3.5 loop. Each loop is lambda over 2, is the length of the tube. So from here, your lambda is 4L over 3. And then your frequency is going to be V over 4L. And then I flip number 3 up to the top. Okay. And then I do one more twist on this. Bam, bam, bam. Bam, bam, bam. There you go. So this is 2.5 loop. So I can write it as like 5/2. But now you start to be able to guess. We did this like a couple times. So you know that now you just get the same result, except now the number 3 turns to number 5. So you start seeing that your lambda in each resonance, the first resonance is L, is like 4L. The second resonance is 4L over 3. The third resonance is 4L over 5. And that will lead you to the frequency of 5V over 4L. Okay, so with this, then your fundamental frequency is V over 4L. And as you can see, your third resonance is 5 times that. So let me draw a conclusion right here. So this is your third resonance. But here it's 5th harmonic. Yes. All right. So the harmonic is focusing on the frequency, right? So it's focusing on the frequency of that value, how many times that it has to multiply the fundamental frequency. If it has to multiply by 5, that is going to be your fifth harmonics. Okay. And for the number of resonance, you just count from the first one. First one is the first resonance. The second one is your second resonance, on and on. All right. And okay, if you like, this is your, sorry. This is your, what did I do? Oh no. Okay, so let me do this. Let's screen again. Sorry. Just hit the. All right, and I can say this is also your second overtone. All right, that is done. It's like naming is confusing, but that's what it is. All right, so it's a third resonance. So that's the third situation that you will be able to generate a standing wave counting from the fundamental one, but it's a second overtone because that's 2 steps from the first. But in terms of the frequency, it has to be 5 times the frequency of the fundamental one. So that's why this is going to be your fifth harmonic. Okay. I hope this clear up things a bit.
Yes, thank you.
Okay, Cap. Very good, very good. I hope this is useful.
Excuse me, Ajahn.
Yes, go ahead.
Can you show me how to do question number 4 for this set? I
Okay.
don't think I understand it pretty well.
Okay. This number 4 right here, right? The one.
Yes.
Okay. All right. Sure. Okay. Let's see. So we have a light string of mass m. Okay, and the length is given. Everything is good. It has n times to 2 walls separated by the distance d. So there's a little bit of geometry has to be concerned with. Now, 2 objects, each of mass m, are suspended from the string as shown in the figure. Okay. So if a wave pulse is sending from point A to point B, how long does it take? Well, this is a very good question, actually. So if you just want to generate a wave traveling along this string, okay? So first thing first, the one that we always use and we didn't really care so much about proving it is just say you are able to calculate the speed of wave in a string by using this relationship right here, mu t over mu, where the t is just your tension and the mu is just mass per length. Okay, so you guys with me with this. Okay, this is good. Alrighty, now, so the key is if you know the velocity of the waves, so you will be able to determine the time traveling from A to B by just saying that the time that you want, let's say, let's call it delta t, is going to be equal to the distance that the wave has to travel, which is L over 2. That's the distance from A to B. Okay, so far so good. So that's, let me highlight that one. This is the path that it has to travel from A to B. So it's L over 2 divided by the speed. That's it. So the only thing that you need for this one is just try to figure out what is the speed V. And because it depends on the tension, okay, then the mu should be easy to figure out because the mu is mass per length. And because they already said, let me make sure that I get this one right. Okay, the light string of mass m and length L. So that is going to be m over L. So at least the mu part is pretty much done. Right? It's already given. That information is already given to you. So the only thing left for you to figure out is what is the tension in the string. So let's focus on this one a bit. And then now we have to utilize the techniques of doing that free body diagram a little bit. So if you focus on point A, okay, and then you see what are the forces acting at this point. Because from the look of it, you have three strings pulling apart. So there'll be a string on this side, that and there's a tension on that side pulling up, this one pulling to your right, and this one pulling down. Okay, the one pulling down, this is not too bad because it's coming from the mass. So that must be mg that's trying to pull down. Okay, and then now the only thing left for you is you want to figure out the t. This is your t that you want to plug in into your expression on the right. But then you still have another t. So let me call this a t prime for that one. Okay, so now you have two unknowns at this point. You have t prime and the t. So it seems like you have to somehow solve for this a little bit and see how it goes. So what you can do for this one is you can break the t into two components. The one that is already sort of like diagonal. So you want to put them in x and y directions. So you can call this one up right there. And if you want to call this one theta, so this up component will be t prime cosine theta. And you have t prime sine theta on your left. Okay, so far so good. So from here, you will be able to write the equation over here. Okay, let me sort of change the color a bit. There you go. So from here, then you will say, look at what is going on the x-axis. You will see that t prime sine theta is equal to t. And when you look at the vertical axis, your t prime cosine theta is your mg. Okay. And from here, because you don't care about the t prime, you don't want to know that tension, you just want to figure out the t. So I can just take these two equations and then you can divide them to eliminate the t prime. So what I can do over here is just take 1 divided by 2. That will give you the tan theta equal to the t over mg. Almost done. All right. Now, what is going on with the theta? All right, theta is not bad because if you look at this one, you pretty much know, I think you know the dimension of this already. Okay, let me zoom out a bit. So let me draw that triangle over here. There, that is your theta. Okay, so your theta will be the opposite over here over hypotenuse. And then now the number is going to look a little, well, not too bad. Okay, so look at this side first because the whole length is d. And then this length of the string is only L over 2. So I will be able to figure this out. It's going to be d minus L over 2. And then I divided by half. You guys with me? Because there will be another similar triangle on the right over here. Okay, so this is going to be the whole d, the whole length between walls. And then you subtract out that yellow highlighted portion. Is going to be d minus L over 2. And then I split this in half, left half and the right half. So this is going to be over 2. Okay with me so far? Alrighty. And the annoying part will be the adjacent that you need Pythagorean theorem there. So let me highlight that part. It's going to be this blue highlighted length there that you need to figure out. Whew. All right, that's gonna be, am I doing it right? I think so. Okay, so that's L over 4. I already drew this one on top, so I don't know, am I referring to the right length? Okay, that's L over 4. Okay, so then you have to figure out that length, the blue shaded length over here. Let me put it out here. You want this length, and this length coming from the Pythagorean theorem. So you take the hypotenuse along with that opposite right there to figure out the blue. That's gonna be bad. But anyway, all in all, you will be able to figure out the theta. That's my whole thing. Right. My whole point is you will know what angle should be. So that means your theta is known over here. So this one is fine. So this one's checked. Or I mean, tan of the theta is known. It's the opposite over adjacent. So that means your tension is going to be mg and tan theta that you just got. And that is a long one. Okay. All right. So let me write it like this. The tan theta over here, mg, is just the red over blue. Oh, sorry. That's not what it is. Here. You guys with me? Yeah? The tan of the theta is the red over the blue. Okay, right there. That's your tan theta. All right. Once you have this done, then you can just plug this thing back into your original expression right there. And that expression just go all the way here. And that is done. Okay. Is it good? I hope this works. All right, without going into the detail of how to manipulate all those terms in the mathematical equations and everything, I hope this sort of show you all the steps that need to be taken to get to the, I got t equal to mg over 10 x. Oh, wait. Mg over 10. I think it has to be mg multiply, I think, because let's see if I'm not doing anything wrong here. The t sine theta of mine is equal to the tangent t. So this first equation is checked. And the vertical components, the t prime cosine will be equal to mg. This one is fine. Then I just take these two and then just create a ratio. So it's going to be t over mg equal to 10. Yeah, so I think t is mg times 10 theta.
I use different triangle.
Oh, okay, that's fine. So if you pick opposite angle, let's say you define maybe the bottom one, that will be fine. So it's everything will be opposite. So, all right,
Okay.
like your x, right? For example, maybe your angle that you use could be, let me write it maybe like this one. Okay. And that will be opposite ratio. Yeah, that will be fine. Yes. Not a problem. But you got to get the same results anyway. Numbers, I mean, the expression looks pretty dirty though, because you need Pythagorean theorem a little bit. Yeah. Okay, cool. Yeah, this is kind of nice. Like the dark background. Well, maybe, I don't know. Is the white background or the dark background is better? I don't know. Like everyone seems to sort of implement dark mode right now. So it's kind of cool. All right, next question. But the material on the second part of the exam seems to be okay for you guys. Seems like doable, I think. I hope. All right. And look at the numbers of audience today. So I think maybe it's not as concerned as the first one, I guess. So it's a good sign. It's a good sign. First. Okay, so set 5, problem 3. You have a 50-gram object connected to a spring with a force constant given, okay, and it's oscillating with a given amplitude. Assume no frictions, okay, and it's in the horizontal surface and everything. Okay, what is the total energy of the system? And then you have to figure out the speed of this position, the kinetic energy, and the potential when it's at some particular position. Okay, so for this one, I think there are a couple of ways that you can approach this one, but the key is, you know, the mass of the object is a 50 grams. So let me turn this into kilogram. So it's going to be kilogram. Okay, so it's 0.05 kilogram. And the force constant is given. So you know the K of the spring, 55 Newton per meter. Okay, and the amplitude A is also given to be 4 centimeter. So let me turn it into SI system and everything. Okay. Now, so what is the total energy of the system? Because you know the amplitude, you know the K. So we know that at the, I mean, you can either figure out through the speed or through the potential energy, right? So we know that it's just the conversion between potential energy back to kinetic energy, and then it's go back to potential energy, and it's just keep going back and forth. So at any particular time, okay, so at the most stretched configuration, that's when the displacement is equal to the amplitude. At that point, your total energy will be stored in a potential energy, okay? And that is going to be 1/2 K amplitude square. You guys, again, you with me on this one? Okay, so it's 1/2 Ka square. So when this is the case, then you know everything. So this one is done. All right.
Yeah.
Now, part B, the speed when the position is at 1 centimeter. So what you can do is, okay, if you want to sort of like derive this in a way, oh, I just have to go up one more page. Okay, so in part B, because you know then when the position is 1 centimeter, so your potential energy, okay, let me put this one as U max. This is maximum potential. Okay, so now when you are at 1 centimeter, your potential energy is going to be 1/2 K, and it's going to be 1 centimeter, which is, I turn it into 0.01 meter square. So this is the amount of energy that you store in potential, right? So the rest has to go to the kinetic energy. So your kinetic energy will be the rest of the energy. So it's going to be U max that you already found out in the part A, subtract out the U here that you just got here. Okay. All right. So once you have this number, you equate this to 1/2 mv squared. And that's how you figure out the speed at this point. Is it good? Okay.
But Jan, why do we sometimes in the Google they use square root K over M times A square minus X square? Well, I'll write it down.
Yeah, very good. So that is a formula that we also have in our class. All right. And that's a shortcut because if I am writing this one down, okay. So what's that expression again that you found from the internet there?
Square root
Okay.
K over M
Okay.
bracket
Square.
times bracket. Yeah.
Is that
Another
square?
bracket. No square, no square.
Oh, no, square. Okay.
Times A square
Okay.
minus X square.
Ah,
It's a
and then
bracket.
that one, right?
Yeah.
Okay, so that is fine. Omega A square minus X, and that is your speed right there, right?
Yeah.
All right. Now, look at this one that I have over here, this equation. Okay, U maximum. Here, let me write it in green here. U maximum here, that's 1/2 Ka square. U is 1/2 K, wherever X you want. Okay, and the rest of the equation is 1/2 mv squared. All right. And now those all have cancel. I can divide through by the m. So that means I'm going to have K over ma squared minus K. Okay, I think I have this bracket over here, right? Is that what you have here? Yeah. Okay, so K over mx squared equal to v squared. And now you see that I'm getting the same expression by just taking the square root and pull out the common factor K over m. All right, does that help?
Oh, I see. Yeah.
Yeah, so it's the same thing pretty much. It's just, I think by explaining to you how to get to the kinetic energy by finding out the portion of the energy that's stored in potential form, then the rest has to go to the kinetic form. Then you don't have to sort of like memorize the equation or the formula or anything, but you get the same result anyway. Yep, right there. Same thing. All right. And the same thing goes with the part C and part D. All right. They want to find the kinetic energy. So when you have this, then my approach seems to be applied, seems to be like a direct application to part C as well. So part C will be a straightforward way that you can do. Here we go. So part C, they want to figure out the kinetic energy and potential energy when it's positioned at 3 centimeter. So you know right away right here, it's going to be 1/2 K 3 centimeter, which is 0.03 meter square. So that is a portion of the potential energy, right? So now you know that the rest has to go to the kinetic energy. So your kinetic energy at this point is going to be U max minus U, and then you're done. So that's make it even easier actually, part C and part D. Yeah.
Is that not the same as part B?
Part B, they're asking for the speed. So that's why you have to take the square roots. But for C and D, they only stop at the kinetic energy. So you don't need to go deeper into your 1/2 mv squared. Does that make sense? Because up here, you have to go to the 1/2 mv squared expression to dig into the velocity in here. But part C, all they need is just they want to know the kinetic energy. So you don't have to use 1/2 mv squared on this one.
Oh, okay.
Yeah, it's just actually easier. I mean, just less number crunching steps and all this stuff. You can just find the difference between the maximum energy and the potential energy at 3 centimeter, and then you know it's the rest that goes to the kinetic energy for sure.
Okay, I understand now. Yeah.
Okay, all right, great. Yeah, cool.